We've got a special opportunity for you today, or a special presentation today. Of course, we're at the Tom and Lonnie Show. There's my friend and colleague, Dr. Lonnie Love, over at Sandia National Laboratory. And we've got, of course, our other host, Stephen Lamarca from AMT. Hi, guys. Good to see you. And today, we've got a special guest from Lincoln Electric, Patrick Wallen, and he is going to talk about some of the really cool stuff that they have on large-scale additives. So, Stephen, I'm sorry, Stephen, well, you could say hi too if you want to, but Patrick, I wanted to turn it over. Yeah, hi, Stephen. Patrick, I wanted to turn it over to you to sort of talk about some of the really cool stuff on 3D printing, additive manufacturing going on at Lincoln.
Okay, great. Yeah, thanks. We've got a lot of things going on. Let me shut this door quick. Sorry. Yeah, we got a lot of exciting things going on at Lincoln, and it's not a new journey. It's an old journey, but it's starting to accelerate rapidly at the moment, and for the last year or two. At Lincoln Electric, we're the largest, oldest welding company in the world, and a big focus for us has been automation. So as a company, we make welding wires, we make welding machines, and we've really made a concerted effort to invest in technologies around our automation and metal manufacturing business. Over the last decade, we've acquired a number of companies, invested hundreds of millions of dollars in accumulating and integrating different technologies that allow us to fully automate manufacturing facilities and bring to bear the latest control technology and closed loop technology to execute the product metal cutting, metal placing, metal welding, and automate in general overall fabrication processes for industry. And one of the offshoots of that is we acquired some companies, one called Wolf Robotics, and we had call it a nascent technology around 3D additive manufacturing. We're working with Oak Ridge, as you all know, on several projects, and ultimately we've combined all of our technologies to give us a fairly unique capability to manufacture components with 3D technology. We use our welding machines that we produce, our knowledge of welding procedures and processes, our own wire that we produce, which is a critical input, where it's a known input that we can manage and control. We integrate our own systems, so we have our own robotics integration technology combined with a proprietary sculpt print technology that we use to translate 3D drawings into tool paths, combined with everything that you need to quickly assemble proper architecture for welding a component out with an arc welder. And then we also have the last step in the process, which is the ability to machine and inspect a finished component and deliver to the customer ready to use a 3D additively manufactured component using wire arc additive manufacturing. So it's at Lincoln, our capability from wire to automation integration to the sculpt print technology and the ability then to machine and deliver an finished inspected component is pretty unique in the industry, and it allows us to control all the levers that are critical to deliver a component that meets the quality requirements of our demanding customers, whether they're in energy or national defense or structural manufacturing.
Tom, you're muted.
Yeah, Tom,
My
you muted.
microphone just told me that. So thanks, guys. It's the first time it's ever happened to me. But anyways, yeah, what I want to point out is actually just really cool before we go to the next slide, which is way cooler than this slide, is much of what we talk about, okay, well, we print something, but, then you got to finish it. And so Patrick's like, hey, we got machining, but they also control the material that goes into the printer, the robots, I mean, everything. So it's sort of interesting how all of this came together and the real capability here. So are you ready for the next slide, Patrick?
No, I got
sure,
one.
Sure.
There's one other thing that I think is really important. Is so when this started, I was at Oak Ridge when this started, and I remember meeting with Tom Matthews, and first thing is Lincoln you're like 120 years old or something. It's an old company. And when you start thinking about it, it's like you guys started when like electricity started. I mean, it's absolutely
right.
and you do not weather that long without being really, really savvy in terms of business. And I'll never forget having a meeting with Tom, and I was really excited. We signed our CRADA, and I'm really excited. And I said, "So when are you going to start selling machines?" And he goes, "We're not yet." And I was like, "Why?" And brilliant. He said, "We don't understand the technology yet. And if we roll this out, we're going to have more problems. We need to learn. We need to learn." And I had so much respect for Tom and Lincoln because it was like you understood that you were going to invest. And you mentioned the amount of resources that you're investing. I'm really excited about what you're doing and really admire Lincoln as a company. This and I another one that was really funny is I remember somebody once asking me if I thought that additive would eliminate a lot of the traditional manufacturing companies, and I said no. What's going to happen is I think when companies like Lincoln, like Mazak, like DMG, when they start getting into additive, it'll completely transform the industry. And so I'm as a big advocate of additive, super appreciative of everything that Lincoln's doing.
Yeah, thank you. We, of course, we've worked closely with a lot of national laboratories. I'm a product of National Laboratory and Department of Energy in my graduate school days. So there's a special place in my heart for the likes of Los Alamos and Oak Ridge and the like. So, and we do, we partner with, in particular with Oak Ridge on a number of projects. But, as the technologies develop, this technology did not exist for wire arc additive manufacturing just a handful of years ago. Bits and pieces did, but a fully integrated capability to actually make a high quality part just really didn't exist. So it's come a long ways. And, when you're introducing a new technology or developing a new technology, we're kind of in startup mode, but we have a very large, profitable, stable backer who's looking at the long term, which is really important. It's important to the proper development and deployment of the technology, but it's also important to ensure long-term stability. So as people, they're making a decision to move certain components, and it's expensive to do that. To this technology, then they want to have some assurance that the people who are going to supply them the components are going to be around in 2, 3, 4, 5, 10, right? And that's one thing. That's one thing with Lincoln Electric that you can be sure of is that we have the ability to and the financial balance sheet to scale, but also the stability over time as a large multi-billion-dollar public company that we're going to be around. So, for example, the Navy or Chevron or, big energy companies, as they're making these investments in integrating the new technology into their portfolio of products to service their facilities or to build new equipments, submarines, aircraft carriers, whatever. They want to be sure that somebody's going to be around to supply them in 5 years or 10 years. And as you know, like for example, in defense, there's been ups and downs. The industrial base is contracted or expanded. And Lincoln has always been around. We've been through all the ups and downs, and we continue to be here, and this business will be too. So that's it. It really is an important aspect. Also, because it is a new technology, we wanted to control, like Tom said, we wanted to control the rollout,
Right.
Yeah.
so that we don't provide unrealistic expectations about performance before we have all of the knowledge of the materials. Because it's not just about building, it's about material science. It's about knowing how the materials are going to perform based upon the procedures that you use, and ensuring that the customer gets what they're looking for in a performance of the components over the long term. And that's also an important aspect of why we wanted to control this rollout of the technology, so that there's only a good experience with our systems and our components, and not a bad experience in the marketplace, because it is an important technology. This digital foundry, rapid scalability, rapid response type technology is going to be very, very useful to the overall U.S. industrial base over time, for sure. So
Definitely. Yes. Yeah. And I got to say, it's like, this is right on the money, but I'm so stoked because I've got a little preview of what slide is coming next. Right. So I definitely want to get to this next slide, because I think
before you do that though, can I disrupt with what might be a silly question?
Sure.
I'm so sorry. But so I think it's really cool how a lot of like at least one form of metal additive today has been an evolution of essentially welding. Like a lot of metal, at least one form of metal additive is basically, CNC welding, but instead of joining parts together, you're building an entire part out of a melt pool of metal, welded metal. Because of this, and because of all of like the technological development in metal additive and all the stuff that companies like you guys have done, do you have you seen, or do you foresee a reverse trickling of this technology? So like as metal additive gets more advanced and starts welding or growing parts out of exotic alloys, like GRX 810 or the nickel alloys, do you think that some of that technology is going to trickle back upstream towards manual welding? Like regular welding will be able to weld with like wire of like some more exotic alloys? Did that make sense?
No, I mean, I think I think the materials that are required by industry are the materials that are required by industry to weld in castings, weld in forgings, weld pipes together. Those materials are those materials, right? There's not, it's driven by the industrial demand or by technological advancement in, higher pressures, higher temperatures, higher strengths. So I would say as far as materials and market requirements, they're all flowing one direction, from the welding to component production, if you will, but not the other way around.
So it's not like, if a machinist like totally like crashes a spindle into a pretty maybe not necessarily expensive part, but crashes a machine tool and it's like gouges out way too much material than they had intended to. They can't just go in there real quick with a welder of the same material and be like, let's patch that and then do it again.
Well, you can, yes, but as far as the welding materials and material requirements, that all comes from the industry. And whenever the steel mills are developing new technologies, they're always looking at, well, how can it be used by industry? Is it weldable, right? Like any technology, that's one of the things. If you're going to make a steel, it probably needs to also be weldable. So, some things aren't weldable, and then they know that, but there's specific applications for it. So yeah, definitely, it comes from the welding. And then if we're using wire for additive to create a component, the advantage is that it's all weld metal. So then when you go to weld it, it's absolutely imminently weldable. The same can't be said necessarily for castings, in particular, right? So there is a big advantage with additively manufactured components using arc welding, this WAM technology, because it's weldable because it's welded. So there was one other thing I wanted to say about this slide, and that is important, is that at Lincoln, if you want to have a production facility, you need to have the capability to run 24/7. And in order to run 24/7, you need to have a certain scale. So as people look at, unless you want to tinker, then if you want to have a production facility, you really got to have a certain amount of scale, because you got to run 24 hours a day, 7 days a week. So, and we have that capability in spades in our facility.
Yeah, it is very cool. All right, let's get to some cool images.
Yeah, so you can see. So we've got a 75,000 square foot facility in Cleveland. It's roughly half full now, maybe a little over half full with systems. We have two primary systems. We have what we call our Series 2, which can handle 1,500. So there's a robot, 6-axis, with a tilt rotate table, sky hook we call it. And there's two scales of that same robot. We use ABB technology in our additive systems. But in the future, we have the capability to use anybody's robotic arm. But for now, we use ABB because it gives us certain advantages in combination with all our other technologies that we deploy. But we have the Series 2, which has a 1,500 kg table. Or you can see there's a plate located directly under the robot base where we can fabricate vertical builds of up to say 10,000 pounds, 15,000 pounds directly on the plates. And then we have a larger scale technology that's a Series 3, which has a 10-ton sky hook. And that was specifically deployed for certain large structures for oil and gas and for defense applications, primarily around submarine type components. And we have 4 of those systems deployed. We're also deploying a new Series 4, which is a scaling up of the Series 2, which has the 1,500 kg skyhook. So now we're installing another 4 of it's gone from 1,500 kg to 5,000 kg. So a 5-ton skyhook, which we'll be installing as standard going forward. So 3 capabilities depending upon the size and scale and scope of the components that you want to manufacture. And again, we're operating 24 hours a day, 7 days a week. We also have 2 systems installed utilizing hot wire laser, one of which is more dedicated to call it cladding type applications. So you can additively manufacture and we can use laser cladding either as welded or post machining. And we also have a new system that we're deploying using our proprietary, again, hot wire laser with a specific concentric head for additive manufacturing. We're going to explore hot wire laser uses with, it's an 8 kilowatt, so we've got a lot of energy. And in certain types of crack sensitive materials, there might be some advantages to utilizing the hot wire laser. So we'll be exploring that as well with the technology that we have deployed in our facility. Today in our facility, we have roughly about, say 45 people. I would say 25 are engineers or physicists, or probably half have PhDs. And all of our operators are welders. So, we've got metallurgists, we have mechanical engineers, we have software engineers, obviously. Like I said, a whole lot of them are PhDs, and the ones who don't have PhDs should have PhDs. That's my opinion, right? But then We more welding companies. We make sure all our people know how to weld as well. So that kind of gives you a flavor for what we have in our facility. We're expanding. We'll expand out to probably 50, in between 50 and 60 systems in this facility, and from there we can grow rapidly. The ability to scale for us, because we make all of our own systems. So those systems you see there, everything in that is fabricated by Lincoln Electric except for the ABB arm. So the sky hooks we make, the integrated fume extraction we make, the welding power source we make. Okay, the roll down doors we don't make, but I think you know what I mean, right? So pretty much everything in there you see is made by us.
Cool.
You want to see the yeah, any questions on any of that?
I think it's cool. I want to show them what you're making.
Yeah. So kind of where we started. Go ahead, go to the next slide there.
You got it.
Yeah, so you know the old saying, you eat your own cooking, before you serve it to somebody else. So a good way, we have, we're a $4 billion company. We have a massive equipment and consumable manufacturing facility across the road, and they have maintenance needs. We have equipment that we've had for many decades. And when things break, and the last time you bought a casting was 50 years ago, it can be very expensive and take a long time to get a replacement casting. So you can see here a few use cases where we have either taken a 3D scanner and scanned, reverse engineered and scanned a component that broke or fractured, and we'd rather not replace the cast iron or casting with another casting. So we simply brought it over to Additive. We scanned it with a scanner, turned it into a 3D CAD drawing, and then translated that into our closed loop sculpt print technology, and then printed the component to go back into production. So you can see there, we've got a mixing blade, so that the part on the left was the housing for the blade. The blade also mounts into that, and we for design for additive manufacturing, that kind of funky mixing blade that you see there, we use that for mixing up the chemicals and silicates for our sticky electrode production. And that's another component that broke. So we needed to fabricate a new one. And typically those are solid cast, and then we gun drill cooling channels. So with additive manufacturing, we were able to integrate cooling channels into the actual mixing blade itself, saving us time and energy in replacing it. And we got it versus a casting, probably in about 10% of the time. We also have, you can see on the right, that large barrel shaped item that's a 8,000 or 9,000 pound replacement barrel for our high pressure sticky electrode extruding. So we rather than replace a casting that had some emerging cracks in it that was very, very old, we simply printed it from the floor with our additive manufacturing systems, and that all those components are in production and have been in production for a couple of years now. So again, just proving out the technology, going big or going bigger, using all the tools, whether it's scanning for reverse engineering, or changing a design for additive, or just simply trying to go fast, because when things break down, we can't make product, and there's a big pressure on production. So all great cases for us, and all those components are performing as good or better than anything that we could have bought outside. So, and we continue to do that today. We're constantly building components for the factory, just because it's cheaper and faster to do it that way.
Nice.
So the next slide, a couple of really interesting areas, in particular for the U.S. Navy and the DoD, the industrial base. We as everybody knows, there's a lot of pressure on naval assets today. There's pressure from the east. There's pressure from the west. And we don't have enough assets. We don't have enough aircraft carriers. Don't have enough submarines in particular. And they want to build them faster, but one, we've got to get the people, but two, we also have to be able to manufacture all the components. And of particular need within the Navy, as we're talking about here, the Navy is replacements for castings. Castings, especially for some of the materials that the Navy uses, they're very difficult materials to cast and cast with a reliable quality. And this case was a case where the lead time was too long. And as you're building a complex structure, subassemblies have to be moved, they have to be integrated, and you can't hold up a whole ship build or a move of a structure if you're because you're missing one casting, right? Which means later on you got to try and shoehorn it in somehow after you've put the sections together, as an example. Well, this is a case where the Navy came to us about 3 years ago. They were going to have a delivery problem. They needed to get the hinges for the reactor doors installed so they could do the subsequent sequential production, and it was going to be a big problem if it didn't get done. So we used our emerging additive technology. We printed out of the high strength material called MIL 100S. It's like a HY80 type material, a very high strength, high toughness material. And we printed two sets. We machined the ones, both sets. They destructively and mechanically tested one set, and the other set was installed in CVN 80 after passing all the requirements. That kind of opened the door and opened the eyes because of the Navy to what our technology actually is capable of with, a difficult material like MIL 100 to perform. In fact, outperform the castings that would have been used. And subsequently, they've ordered another set for CVN 81, which we completed a couple months ago and we shipped out. And I anticipate from here on out, they'll be just ordering additive components for that critical application. From there, and that was a Newport News application. From there, because Electric Boat and Newport News work very closely together, there's a lot of submarine applications we've been working on. I'd love to show you pictures, but generally we don't want to go through those pictures in a forum like this. But some key materials, copper alloy materials, copper nickel, nickel aluminum bronze, 625 and 316 for the propulsion side, reactor side components. We're building components up to 7,000 pounds. We're about to start one out of 625 that's around 10,000 pounds. Of course, MIL 100, which is a high strength alloy for replacing all of these things, for replacing complex castings that are proving to have lead time and quality challenges for the Navy, given the current production rate, and they want to accelerate the production rate significantly. So with our technology, with our capability, with our ability to deliver a high quality component, with our core technology, we're kind of the best horse to ride, if you will, if they want to scale and they want to be able to do something rapidly. Because we make our systems, because we're $1 billion automation company, we can rapidly scale to deliver what the Navy's looking for in the coming couple of years.
So nice. Patrick, there's a material I'm really interested in that a couple of years ago.
Tungsten?
No.
All right, never mind.
It's going to be stupid. It's stupid. Aluminum. And you go, well, why would you want to print aluminum?
Yeah.
Everybody I'm working with right now wants a lot of printed aluminum.
Yeah.
Because the submarines, the submarines need the titanium, the HY80, HY100, but the submarines have one main purpose, and that's to deliver a certain payload. And those payloads are usually just big aluminum cylinders.
Yeah.
And right now, we can't get them. We can't get them. And so here's an interesting thing. So I was at Weber Metals out in Long Beach about 2 months ago, and they're showing me this big forging press because we're using them to try to forge some of these 7075, 2024, 2021 aluminum forgings. The lead time is forever. The forging press cost them $200 million. It took them 5 years to install. Took them 5 years to install. The base is 3 stories deep underground. It's incredible. It's incredible. 60,000 ton press. And I'm sitting there going, if you could just get me aluminum cylinders, 8 inches in diameter, 12 inches in diameter, 4 feet, 6 feet tall. I just want cylinders. And it's actually a pretty easy problem. Now your layer times, I just want cylinders. It doesn't have to be complex. You replace that $200 million forging press. And right now, the forgings we're spending on some of these vehicles, we spend probably close to, I'd say, $100,000 on just the forgings per vehicle. And then we machine the living daylights out of it. And that's why I want a cylinder. All right, solid.
Right. Aluminum hasn't really been our core focus, if you will. Like, of course, we melt. We have a melt capacity, so we from melt to finished wire, we make aluminum wires, right? Because we're a welding company, and not only that, we also melt in the raw materials in our Indalco facility in Canada. So depending on the alloy and the weldability, the alloy and the mechanical properties of the welded aluminum, because typically a welded aluminum is inferior to the original material. So we'd have to look at that. We can weld aluminum. It just hasn't really been a focus for us, right?
I understand. I thought it was stupid because aluminum cuts like butter. It's usually pretty cheap. But when I was at Oak Ridge, I was all about technology trying to push technologies out.
Right.
My job at Sandia is the exact opposite. It's mission pull. We have to deliver on systems.
Yeah, speed and time. Well, we should talk about that. Yeah, right.
Speed and time.
Right, exactly.
And right now, and even on the forging sides, we're having some real issues just on repeatability. Right. And so have you guys started looking at, can you get to forged like properties? I think it's easy to get to cast like properties, but especially if we kind of bound it as like, if you can just give me a cylinder,
I think
your layer times are the same.
Yeah, I mean, if you think about not aluminum, right? But first of all, everybody assumes a forging is super clean and perfect and the best thing in the world. Yeah, well, guess again, it isn't always the case, right? I mean, we all know what castings are, but forgings aren't a panacea. But
I'll tell you a funny story. So I was at Weber and I'm watching them, and it's like they got this big furnace, so they got this forklift and they chuck this big ingot into the furnace. They're like, yeah, it's about time. Pull it out, and they just start whacking the crap out of it. And they got a guy with like one of those weed eater spray bottles, and they're an amazing company, but they're spraying on this lubricant. And Suresh Babu, I'm telling him, and he sends me a video from 1907. It looks very similar. So,
well, we should talk about that.
All right. So that might be a topic for next time. I know we're kind of running over here, but let's get to your last slide. And
all right, let's hit the last slide. Stuff. And it's another important use case, right? This is again, speed, quality, and capability. And another case here. Now, this is a refinery case. This is a nickel component. They came to us with a requirement. They had an outage. As happens in outages, they were having a look at a critical maintenance component, and it was in worse shape than they anticipated. They came to us, and within a matter of weeks, we had, within a couple of days, we had started printing. Within a couple of weeks, we had managed to produce components for them, as well as components that were produced for testing. And at the end of the day, the components passed, met the requirement, and was installed in a refinery and is still being used in a refinery today.
Awesome.
And the kind of the cool thing, right? We were talking about it's made of welding material additively in our technology, and now you need to join that. It's not a casting. Now you need to join it to pipes and to uh, other connections have to be welded. So it's easy to weld because it's weld material, and that also provided a significant advantage for them. So again, met the criteria, met the requirements. Everything was tested all in parallel, and validated by a third party testing house, and Chevron installed it, and away we go. So we've installed other components. We've made other components that have been installed in refineries today. So this is another important area for us. Those critical turnarounds that can cost, not only if it costs the refineries money, it's costing the consumer money at the end of the day. So bringing that fast response time, the high quality deposit, whether it's a nickel casting. The other thing is because we're a welding company, we had the wire rod in stock, and we were able to pull it out of our wire rod inventory, turn it into wire, send it over to the additive facility, and start fabricating literally within hours. And because we're end-to-end in fully integrated company, we were able to do that, and we had the material in stock. Otherwise, you might have searched for 30 days just to find that specific material, but we had the rod in stock. So that's one of the other things that really, really sets us apart. So again, a very successful case here.
And I think that's really important, because when we were over at Oak Ridge, we actually had a similar type of project where we needed a very specific wire for making something, and I think we probably used up more than half the wire available in the nation, for that one. Yeah. So if we had to make two parts, we could make two parts. But again, I think what's really cool is you guys have the whole supply chain. So we need to do this. Right. We can scale it up and have access. Anyways, very cool.
Right. Okay. Well, great. That was fun, Tom. Lonnie, I really appreciate that, Stephen. It's a good chat. So I'd love to, we'd love to contribute other content, talk about other subjects. We've also got automation subjects as well in the long run. So we'd love.
There's definitely room for there's enough left on the table for an episode.
We'll get you back. Now, are you going to have any of this stuff at IMTS next year, or in 26? Yeah.
I think so, yeah. And I should mention next week is a Fab Tech show in Chicago. Oh, yeah. So some things will be there from the automation side, some of the new technologies that we're deploying that are pretty exciting. We should do an episode on that too. That there's some really, really cool stuff that, like we've talked about, I think, in the background on our abilities to drive kinematics of robots ourselves, which are going to open up all kinds of interesting opportunities for us to add more tools to our closed loop technology to manage automation as well as 3D additive print technology going forward. So there's a lot of exciting stuff we're working on, and a lot of it started with you guys. So we're all in the same team, all from the same boat, all going in the same direction. So I'd love to do this again, and get some of my team members, also to get on some of these podcasts when you want to mix it up with us again. We're happy to do that.
Awesome. Outstanding. I think it's awesome. And I think I'll just point out. So this is, people think, 3D printing, hit the print button, you're done. There is so much that goes on, from the materials to the robotics to the planning to the CAD and CAM systems and so forth. So it's just awesome. Well, listen, thanks so much. And again, by the way, another reason to come to IMTS next September, in fact, I think we're going to get Doug Woods on here for our next podcast. That puts a little pressure on Doug to make sure he does show up for our next podcast. talk about, some of the things we're going to see over at IMTS in Chicago in 26. So, hey, Patrick, thank you so much. Great seeing everybody.
Thanks
yeah, good seeing you all.
All right.
See you, Lonnie. Good seeing you again.
Stay safe, everybody.
All right. Thanks. Cheers. Bye, gents.